And I think I did not post the 11 o'clock recording on Tuesday. So let me make myself a note, because I did record it, the review, and I can post that to Blackboard. Okay. Wrote myself a note. Post it. I'll put my post-it here where I can see it. All right. So today in the college algebra class, we are going to start discussing absolute value and inequalities. So it's probably a good idea to do a little quick review. We are going to review in the 12:30 period also inequalities, but it's probably not a bad idea to talk about them a little bit here also. So first of all, on Tuesday, we talked about the absolute value. And the way you represent an absolute value of a number is you put bars around that number. And by definition, the absolute value of a number is just that number if that number is 0 or positive. So for example, if we take the absolute value of 3, that's just 3. So if you take the absolute value of a positive number, you can just remove the absolute value symbols and it's just that number itself. But if that number is negative, and that's the way we represent positive and negative. Looking at my number line, if a number is to the left of 0 on my number line, then it's negative. So the way we represent that is we say that number is less than 0. That's what that means. So if I have an A and I have that arrow symbol pointing to the A, and then we have a 0, that means that number is less than 0, or that number is to the left of 0 on the number line. And to find the absolute value of a negative number, we change its sign. So the absolute value of -3 is technically, we change the sign of -3. And what happens when you change the sign of a negative, you get a positive. And I probably should talk about the other inequality I wrote up there. The other inequality I have is greater than or equal to 0. And what's that mean? I have A with an arrow pointing to the right, and I have a bar underneath it. So the arrow part that points to the right says you're greater than. So that means that we're going to be to the right of 0 on the number line. Well, what numbers are to the right of 0 on the number line? The positive numbers. And that bar underneath it means that it could also be equal to. So if A is greater than or equal to 0 means it's 0 or to the right of 0. It can be one or the other. I was going to say something else and I forgot. All right, so again, the way we represent positive and negative numbers on the number line positive numbers are to the right of 0. Negative numbers are to the left of 0. So negative numbers are less than 0 to the left, and positive numbers are to the right of 0, to the right. So an absolute value of a positive number is just that number. But the absolute value of a negative number, we have to change its sign. And that's what the negative in front of the A means. So if it's a negative number, we find the absolute value by changing the sign of that negative number. We make it positive, if you will. Okay, so a lot of explanation just for the absolute value. An absolute value is defined to be a distance. I'm going to put another slide in here. Give me just 1 second, please. All right. Okay, an absolute value is distance. And when we talk about distance, distance must be positive. If I tell you to walk a mile, the distance you walk is a positive mile. You walk a mile. Even if you walk backwards, you're still walking the distance of a mile. So distance is always positive. Now, direction can be positive or negative, but the actual distance is always a positive quantity. So distance is always positive. Even if you walk backwards, the distance you walk is positive. The direction you walk may be negative, but the distance you walk is positive. Okay, so if we look again at the absolute value, this is defined to be the distance for is from 0. So if we look at the number line again, there's my 4 right there. There's my 4. And how far is 4 from 0? Well, it's 1, 2, 3, 4 units. So the absolute value of 4 is 4 because it's 4 units from 0 on the number line. Okay, what's the absolute value of -5? Well, I know how to find that from the previous slide. I changed the sign of the 5 and it's 5. So the absolute value of -5 is 5 because of that rule. But it's -5, again, because of the number line. Here's -5. What's the distance -5 is from 0 on the number line? Well, 1, 2, 3, 4, 5 units. So since -5 is 5 units to the left of 0, it's 5 units away. The absolute value of -5 is 5. So again, how do we find the absolute value of -5? Well, we change the sign of -5. So absolute value is a distance. It's the distance a value is from 0 on the number line. And the way we find absolute value is if the number is positive, just remove the absolute value symbols. If the value is negative, then you change its sign. So you take whatever's inside your absolute value symbols and you change the sign of it. Okay, not to belabor the point, but I'm gonna. So let's say I have, let's use a number we haven't used. Let's say I have the absolute value of an unknown, and the absolute value of that unknown is equal to 7. Well, what two values can I take the absolute value of it and get 7? Well, I can take the absolute value of 7 and get 7. So x could be 7, right? But x could also be -7. Because what two numbers can I take the absolute value of them and get 7? 7 or -7. So who knew something so simple could have so many nuances about it? So we can look at the number line and determine an absolute value as a distance between two numbers on the number line. So find the distance between -19 and -4 on the number line. And you could certainly do this Let's do this one first. Find the distance between -4 and 5 on the number line. You could certainly do this by plotting the 2 points and then just counting what's the distance between them. Well, how many units is that? Well, there's 1, 2, 3, 4, 5, 6, 7, 8. There are 9 units between -4 and 5. So to get from -4 to 5, I have to move 4 units on the number, not 4 units, 9 units on the number line. So since distance is defined to be absolute value is distance, we could also find the distance by taking the absolute value of the difference of these two numbers. So this distance could be found by taking the absolute value of this difference. Or you could write it as 4, 5 minus the -4. So the distance between two numbers on the number line can be found by taking the difference, subtract those two numbers, and then taking the absolute value of whatever that is. So the distance between -4 and 5 on the real number line can be given by the absolute value of a minus b, where a is the first number and b is the second number. So the distance between -4 and 5 is -4 minus 5. The absolute value of that, which is the absolute value of -9, which is 9. So again, you could plot the points and then count what the distance is. That might not be the easiest thing to do if these numbers are really, really far away from each other. You know, counting 100 places on the number line may not be very efficient, but you can always find the distance between two numbers on the number line by just taking the difference of those two numbers. And then how do we ensure that it's positive? We take the absolute value of it. So it's the absolute value of the difference of those two numbers. So what's the difference between -19 and -4 on the number line? Well, the distance is the absolute value of the difference of those two numbers. So I just take the two numbers and I subtract them. So -19 minus -4. Sorry, PowerPoint's not cooperating. Which is -19 plus 4, Minus a minus gives me plus. Negative 19 plus 4 is negative 15. The absolute value of negative 15 is 15. And sure enough, if you were to look at the number line, how many places do I have to go to get from negative 19 to negative 4? I have to go 15 places to the right to get from negative 19 to negative 4. So the distance from negative 19 to negative 4 is 15. And it's always positive because distance is always positive. So how do we ensure that it's positive? We put absolute value bars around it. So what's the distance between, I don't know, negative 20 and 50? I mean, I think you could probably imagine, imagine what this looks like. How do I get from negative 20 to 50? Well, I'm going to have to go 70 places to the right to get from negative 20 to 50. So the distance is the absolute value of the difference in those two numbers. And I can see that that's true. To get from negative 20 to 50, I have to go 20 places to get from negative 20 to 0. And then from 0 to 50, I have to go 50 more places. So I'm going to have to go 70 places to the right to get from negative 70 to 50. It's negative 20 to 50. So there's the distance between negative 20 and 50 is 70. All right, sets. Now you have sets, and they're not mathematical. I mean, a lot of us have sets. If you have a set of dishes, so your dishes match. Dishes match. I don't know why that was hard for me to say. For example, a couple of years ago, if you looked in my cabinet 5 years ago, I had 2 different sets of dishes, neither which were complete. So I had that blue willow stuff that my mother had bought for me some years back. And then I had some that my husband bought somewhere. They had apples on them. But I didn't have a complete set of either one. So my children, my sweet children, bought me a new set of dishes, a set of 12. I mean, it's a nice set of dishes. So I have a set of dishes and they all match, but it's a set. So it's a collection of objects, the set of dishes. I also have a set of silver that my mother-in-law bought me eons ago when my husband and I were first married. She bought me a set of silver. So I have a set of silver, 8 spoons, 8 forks, 8 salad forks, etc. So a set, which you are very familiar with, is just a collection of objects whose, since you know what these objects are, then the contents can be clearly determined. So I know I have 12 plates, 12 bowls, whatever else I have up there. I think that's about all they bought me was plates and bowls. But I have a set of 12 of those. I have a set of china too, 8 plates, 8 bowls, 8 salad plates, etc., etc. Okay, so a set is a collection of objects whose contents can clearly be determined. The objects in a set are called the elements of that set. And the way we denote sets in mathematics is to use braces. And we've done this. We did this in section 1.4 when we looked at number sets. So the first method of listing a set is just by a roster. So you list the first so many elements of the set, and then you put an ellipsis behind the last number to show that that set continues on forever. So this is called roster form, where you just list so many elements. And then the ... helps you see that the set continues. So we could even, the even numbers, even whole numbers. So the pattern needs to be established by the first few elements that you list. and then the dot, dot, dot says the pattern continues on, or you could do odd. So you list the number of elements you need to show the pattern in that set, and then the dot, dot, dot tells you that it continues on. And the dot, dot, dot is called an ellipsis. And if a set doesn't have any elements in it, which it could, a set could have nothing in it. I can't think of a set that I don't have anything. Oh, the set of cups that match my dishes. I don't have any cups that match my dishes. I got dishes, but I don't have any cups. They didn't buy me any cups. I don't need cups. I got mugs everywhere. But so they did not buy me any coffee cups to match my dishes. So the set that consists of the coffee cups that match my dishes is empty. I don't have any. So if the set has no elements, it's called the empty set or the null set. And we represent that by a circle, an O with a line through this. So the way we say the empty set, we can represent that by just using two braces with nothing in them, or we can show it with a circle with a line through it. That means a set that doesn't have anything in it. Okay. So another way of listing sets is just by describing them. And this is called set builder notation. So a set builder notation describes the elements in the set, but it doesn't list them. And the way this is read is we have a brace here. So that's read the set of X. And this bar is read as such that. So this is the set of X such that X is a counting number less than 6. So what are our counting numbers again? Our counting numbers are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, etc. So what are our counting numbers that are less than 6? Well, you've got 5 counting numbers that are less than 6. 1, 2, 3, 4, and 5. Those are numbers that are less than 6. So this set here in set builder notation, the way we describe it, it's a set of X such that X is a counting number less than 6. Well, we could also list that as a roster. That set is also described as the set that contains the elements 1, 2, 3, 4, and 5. Those are the counting numbers that are less than 6. Okay, so set builder notation just describes what your set is, and roster notation actually lists what your set is. Okay, so let's first define something called the intersection of two sets. So if I've got two sets, the intersection of these two sets is written like this. So if you have A and you have an upside down U, so take your U and flip it upside down, that means the intersection of those two sets. And the intersection of two sets are the elements. Remember, elements are the members of the sets. The elements the two sets have in common. So if your two sets have any elements in common, that's the intersection of those two sets. So we can write this in set builder notation that the intersection of two sets A and B is the set of X such that X is an element of A and X is an element of B. So X has to be in both A and B to be in the intersection. So an intersection is the elements of the two sets that they have in common. It's in A and it's in B. So intersection, we use the word and. It's an element in A and it's an element in B. So here's an example. I have two sets and I want to find the intersection. So the first set consists of the elements 3, 4, 5, 6, and 7. The second set consists of the elements 3, 7, 8, and 9. So what elements do these two sets have in common? Can you type that in chat or just take yourself off mute? That is correct. The elements that these two sets have in common, they both have a 3. They don't both have a 4. They don't both have a 5. They don't both have a 6, but they both have a 7. So the intersection of these two sets is the set that consists of the two elements 3 and 7. So that's an intersection. It's the elements the two sets have in common. Right? Now, what we use more frequently in algebra is the union of two sets. So what does that mean? Now, we use a U for union. And in MyMathLab, you will sometimes see in your toolbar on your problem a big U, capital U. That means union. The union of sets A and B, written A, U, B, is the set of elements that are members of set A or set B. So union and or. Intersection and union or. Intersection and union or. It's a member of set A or of set B or of both. The definition can be expressed in set builder notation that A union B is the set of X such that X is an element of A or it's an element of B. Now, the way to find the union of two sets, this is the way I do it. Just list all the elements that are in A. Just list them. Then you go to B. Are there any elements in B that you haven't already listed? And if there are, you add those to the list. So A union B is the joining of the two lists. And we've already done this semester. So in section 1.4, we had the set of rational numbers. All those numbers you can write as fractions. We had the second set, which was the set of irrational numbers, the numbers that you can't write as fractions. And we joined those two sets together, the set of rationals and irrationals, and we got the set of real numbers. So we joined them together. We took all the rationals, and then we took all the irrationals, joined them together, got a set of rational and irrational numbers, all of them together, and we got the set of real numbers. All right. So let's find the union of the two sets that we just found the intersection of. So this is the way I do it. I list all the elements in the first set. And then I go to the second set. And are there any numbers in the second set that I don't have in this list? Well, in the second set, I have a 3. I've already got that listed. I have a 7. I've already got that listed. But there's an 8 and 9 in the second set that I haven't got listed here. So I list those. Oops. So the union of those two sets, we just join them together. And we just don't list the 3 and, I mean, you could just join them together. You could list the 3 and the 7 twice. That's just not convention. You don't list elements in a set more than once. That can get kind of confusing. So we don't list the 3 and the 7 twice. We only list that once. And the 3 and the 7 are the intersection of the two sets. And we don't list the intersection twice. We just take the two sets and stick them together without listing any elements more than once. So begin by listing all the elements in the first set, namely the 3, 4, 5, 6, and 7. Now list all the elements from the second set that are not in the first set, and that's the 8 and 9. And that's the union of these two sets. So the union of these two sets is the set that consists of the elements 3, 4, 5, 6, 7, 8, and 9. And let's list the intersection again. So again, if it's in the union, if it's an element, excuse me, in the union, then it's an element in one or the other sets. So the 3 is in the union because the 3 is in one or the other set. The 4 is in the union because it's in one or the other set. The 5 is in the union because it's in one or the other set. So that's a union. An intersection, it must be in both sets. So 3, 7 is the intersection because 3 occurs in both sets. 7 occurs in both sets. So union, it's in one or the other, and the intersection has to be in both, one and the other. Okay, so reviewing the number systems, we've already talked about this a little bit. The natural numbers, the numbers that we count with, whole numbers, if you take the natural numbers and add the 0, you get the whole numbers. If we take the whole numbers and we add the opposites, we get the set of integers. Rational numbers are numbers that can be written as fractions. Irrational numbers are numbers that can't be written as fractions. And the real numbers is the union of the rational and irrational numbers. Okay, so the real number line, which we are going to use a bunch from now on, and we did allude to this earlier when we looked at the absolute value. The real number line is a graph used to represent the set of real numbers. An arbitrary point is called the origin, that's 0. The distance from 0 to 1 is called a unit distance because it's 1 unit. From 0 to 1 is 1 unit. Numbers to the right of the origin, to the right of 0, are positive. Numbers to the left of 0 on the number line are negative numbers. And numbers increase from left to right. So -5 is a smaller number than 4. And -5 is a smaller number than 4 because -5 is to the left of 4 on the number line. Conversely, 4 is a bigger number than -5 because 4 is to the right of -5 on the number line. So numbers increase in size from left to right. That's a convention that we came up with way back when in the olden days. So numbers that are smaller are to the left of numbers that are bigger, or numbers that are bigger are to the right of numbers that are smaller. Increase from left to right. Okay, we are going to discuss this again in the 1230 period because we're going to actually start graphing these on a number line and then looking at interval notation. But we have 4 inequality symbols. Now, you know what equals looks like. Equals looks like this. So what's the difference between equals and inequality? So what this symbol means, A with an arrow pointing to A and then a B, this means that A is smaller than B. So the arrow always points to the smaller number. So this is red, A is less than B. So A is smaller than B, or A is to the left of B on the number line. And that's how I remember less and left. So A has to be to the left of B on the number line for it to be less than B. So that symbol means less than. If we put a line underneath it, that gives us equality. In that case, A is less than B, or it's equal to B. So this is true. 2 is less than 3. 2 is smaller than 3. 2 is to the left of 3 on the number line. Well, this is true. Certainly, 3 is not to the left of 3 on the number line. 3 and 3 are the same value. So when we put that line underneath it, we say that 3 is less than 3, or 3 is equal to 3. So it satisfies the other condition. 3 is less than or equal to 3. 3 is equal to 3. All right? The other symbols we have are greater than. So when the arrow points to the right, again, the arrow is pointing to the smaller number. But what we say is A is bigger than 3. A is bigger than B. A is greater than B. So that third inequality symbol is red. A is greater than B. A is to the right of B on the number line. It's the larger of the two numbers. So we could say something like, I don't know, 5 is greater than 0. So 5 is bigger than 0. 5 is to the right of 0 on the number line. So if you go from 0 to 5, 0 is the smaller number, 5 is the larger number. The arrow always points to the smaller of the two numbers. And I know some of us say it like gobbles the bigger, I don't know, however you remember, it always points to the smaller. We could put a line underneath it just like we did before, and we could say A is greater than or equal to B. So we could say, 5 is greater than or equal to 5, which is true. 5 is not greater than 5, but 5 is equal to 5. So as soon as we put that line under the inequality symbol, we have equality. So it can be greater than or it can be equal to. And when we compare the size of real numbers, we are ordering the real numbers. We're ordering them from smaller to larger. Okay. So which of these are true statements? What's your opinion? Is this first one a true statement? Negative, it's red. -2 is less than 4. I see a yes. That is true. Why is it true? Because on the number line, -2 is to left of 4. Correct? So if you imagine the number line, -2 is over here to the left of 0, 4 is to the right of 0, so -2 is to the left of 4 on the number line. How about the second one? Is that true or not? It's red. -2 is less than -4. Is -2 less than -4? No. -2 is not less than -4. -2 is to the right of -4 on the number line. -4 is less than -2. So this is true. But what we have written there is not true. -4 is to the left of -2. How about -2 greater than 5? Is that true? No, -2 is not greater than 5. If we look at the number line, however you want to look at it, -2 is to the left of 5. It's not to the right. So -2 is not greater than 5. -2 is less than 5. How about -2 less than -2? True or false? Is that true? It's false. That's correct. -2 is not less than itself. No number can be less than or greater than itself. Can't be. -2 is not less than -2. That's not true. But as soon as I put the bar underneath it, that is true. -2 is less than or equal to itself. So a number cannot be less than or greater than itself. but it can be less than or equal to or greater than or equal to itself. So this is true. Or this is true. Both of those are true. Oh, that's it. I thought I had something else. That's a good place to stop. Are there any questions? Anyone have any homework questions? Okay, so we've picked up inequalities. We've introduced it. We'll continue this discussion in the 12:30 period. And we'll actually take these inequalities and we'll graph them on our number line. And then we'll introduce linear inequalities and how to solve those and how to graph those and how to write those. And then we'll also look at absolute values. So if there aren't any questions, I will let you go and I'll see you back here at 12:30. No questions? All right, we'll see you back at 12:30.